The earthquake and accompanying tsunami provoked the largest crisis that Japan has encountered.
The earthquake and
in the
accompanying
65
tsunami
years since the end of
provoked
World
the
War II.
largest crisis that
And this
Japan has
earthquake
encountered
is the
in the
fourth
65
most
years since the
powerful
end of
earthquakes
World War
in the
II.
world.
And this earthquake is the fourth most powerful earthquakes in the world.
The earthquake in Chile occurred in 1960 of magnitude 9.5. And the two most recent ones were one in Indonesia off the west coast of northern Sumatra, occurred in 2004 of magnitude 9.1.
Sumatra.
And then the Japan earthquake
Occurred in 2004
is the fourth largest. Okay, so this shows the largest peak ground acceleration among the KNET and the KICNET sites was recorded at this station, reaching a magnitude of 2.99 G. And this figure shows the record. And the top one is in the horizontal direction, north-south. And the middle one is east-west. And the third one is in the vertical direction, up and down. And this figure shows the seismicity in Japan. From 1900 to 2007, you can see along this coast, there have been a lot of earthquakes. And big circles are the large earthquakes. Okay, why would we have so many earthquakes in Japan? It's because of its geological conditions. Japan endures 20% of the world's powerful earthquakes because Japan lies at the crossing of 4 tectonic plates. Okay, so this is Japan. Okay, and then we have this tectonic plate, Eurasia plate. And this dark blue is the Pacific plate. And the bottom one is the Philippine plate. And the top, we have the North American plate. Okay, so Japan lies at the crossing of 4 tectonic plates. And this figure shows the movement of the 4 plates. Okay, so the Eurasia plate moves in this direction at a speed of 0.9 centimeters per year. And the Philippine plate moves in this direction at 6.5 centimeters per year. The Pacific plate moves in this direction at a speed of 8.5 centimeters per year. And this is the North American plate. Okay, so the Pacific plate subducts under the North American plate at a speed of 8.5 centimeters per year. And the Philippine plate subducts, going this way, the Eurasia plate at 6.5 centimeters per year. The location of the principal interplate earthquakes, and we would have along the Japan Trench. Japan Trench is this a pink line? So we would have earthquakes along the Japan Trench because the Pacific Plate subducts under the North American Plate. And also along the Nankai Trough or Ryukyu Trench because the Philippine Plate subducts the Eurasia Plate. Okay, so now let's look at what happens along the Japan Trench. As the Pacific Plate moves down, it sticks to the overhead plate, and the overhead plate, Japan is located here, and pulls it down too. This leads to a rapid build-up of huge amount of energy. Okay, so it locked, and then when the stress is large enough to fill the rocks at the interface, we will have an earthquake. The joint eventually breaks, which causes seafloor to spring upward several meters, resulting in earthquake and tsunami. Okay, so when this slips, the brown plate will spring back. Okay, so from the dashed line to the solid line, and it will lift the water upward and then create a tsunami. Okay, for the 2011 earthquake, the fault moved upward 30 to 40 meters and slipped over an area approximately 300 kilometers long. This area by 150 kilometers wide. So these are light red area. The rupture zone is roughly centered on the earthquake epicenter, shown by the star along strike, while peak slip will up dip of the hypocenter towards the Japan Trench axis. This is the Japan Trench. Okay, this is a model based on seismic wavefront inversion. So they use a model to predict or to analyze what happened during the earthquake. Okay, this is a model of the subduction of the Pacific Plate, and this is the epicenter of the earthquake. Okay, this big circle is the main earthquake. The main earthquake was preceded by a number of large foreshocks. Okay, so these pink circles are the foreshocks before the main earthquake, and followed by hundreds of aftershocks. Okay, all these small circles occurred after the main earthquake. The first major foreshock was 7.2 moment magnitude. This circle occurred on March the 9th, approximately 40 kilometers from the location of the March 11 earthquake. With another three, these three with the blue outline on the same day in excess of 6.0. Following the main earthquake, a 7.9 moment magnitude aftershock was reported, at this time followed by another one of magnitude 7.7. Over 800 aftershocks of magnitude 4.5 or greater have occurred since the initial earthquakes. Okay, so these are the aftershocks. And this map shows the locations of the foreshock in pink and aftershocks. Okay, this is a 3D map showing the locations of the earthquakes. And this is the east coast of Japan, and the star shows the epicenter. Close to the epicenter, there are 3 nuclear power plants. And this is the Fukushima nuclear power plants. And this is the Onagawa nuclear power plants. And this is the Tokai Daini nuclear power plant. Okay, now this figure shows the tsunami, and the red line shows a major tsunami. And this figure shows the tsunami wave heights, okay, along the east coast. And this is the these are the measures of the tsunami heights, and you can see as high as 40 meters. And when tsunami occurs, the tsunami waves propagate over the entire Pacific Ocean. Okay, now let's look at what happened at the Fukushima nuclear power plant. Okay, so this is the Fukushima nuclear power plant. This is the epicenter of the earthquake. And there were 6 units in the Daiichi or DE Fukushima power plant, and 4 stations or 4 reactors at the Daini DR power plants. Okay, so we have Unit 2, Unit 3, and 5. The maximum ground acceleration shown in red, and the design basis. They designed the nuclear stations based on this maximum acceleration. These are the design basis acceleration. So 4.39, the actual maximum ground acceleration was 5.50, so exceeded the design value. 5.07 exceeded 4.41, and 5.48 exceeded 4.52. Okay, so the maximum ground accelerations in the east-west direction at Daiichi units 2, 3, and 5 exceeded the design tolerances. Ground acceleration thresholds for automatic reactor shutdown are 1.35 to 1.5 meter per second squared in the horizontal direction, or 1 meter per second squared in the vertical direction. That means the nuclear power plants or the units are designed based on these peak ground accelerations. But when the peak ground accelerations reaches this value, and there's a a sensor to detect the peak ground acceleration. If it reaches this value, then the unit will be automatically shut down. Okay, so when the earthquake occurred, the reactors of units 1, 2, 3 were operating. They were successfully shut down by the automatic system installed as part of the design of the nuclear power plants to detect earthquakes. And these systems are called SCRAM. Although all off-site power was lost when the earthquake occurred, all available emergency diesel generator power systems were in operation as designed. Units 4, 5, and 6 had already been shut down for periodic inspection. So only 2 and 3 were operating at that time. 5 was already shut down for periodic inspection. Okay, now let's look at the tsunami. This is the nuclear power plant, and there's a seawall here. Okay, the plant is slightly higher. If we look at the base level of the ocean, this dashed line, and the seawall has a height of 5.7 meters. And the side level is 4 meters. Okay, and here it's plus 10 meters. The design basis was 5.7 meters. That's the seawall. The first of a series of large tsunami waves reached the site about 46 minutes after earthquake. The maximum height of tsunami was 14 to 15 meters. So obviously, the tsunami passed over the seawall, and the ground level is 10 meters, and it also passed through this. So the station was flooded. Okay, the ground level is 10 meters at units 1 to 4. The units were inundated, flooded by about 4 to 5 meters of water. At stations 5 and 6, the ground level is 13 meters. The units were inundated or flooded by up to 1 meter of water. At the Daini power plant, the design of the seawall is 5.2 meters. The height of the tsunami is 6.5 to 7 meters. And the site level is 12 meters above sea level. But the run-up height of the wave in the main building area reached 14 to 15 meters on the south side of Unit 1 building, with flooding of about 2 to 3 meters. Area on the ocean side, this side, where seawater pumps were located, was also inundated. Okay, this figure shows what happened at the units 1, 2, 3, 4, 5, 6. And this is a Daini 1, 2, 3, 4, 4 units. Okay, the blue color shows the flood. Although the plants withstood the effects of earthquake, the tsunami caused the loss of all power sources, except for one emergency diesel generator, providing emergency power to units 5 and 6. the station blacked out, which made the loss of all instrumentation and control systems at units 1 to 4. And so it affected the safety systems for cooling of the reactor cores and the control of containment pressures. And so now it shows the tsunami comes in, and this is the seawall. It topped over the seawall, comes to the station, and if you look at the tank, okay, here the ground is 10 meters, and the tank height is 5.5 meters. Look at the time, 3:42 p.m. and 3:43 p.m. Okay, so it's already flooded. 3:43 p.m. and the tank was flooded. And 3:49 p.m. Okay, so now you can see originally there were 2 tanks located here before tsunami. And after tsunami, one is displaced to here. And this shows the after the explosion at units 1, 3, and 4. Okay, so as a structural engineer, and we are proud that the nuclear power plants were designed successfully to resist an earthquake, but the problem was caused by tsunami. And if you look at this table, historical data of earthquake-induced tsunami with maximum height above 10 meters hitting the coast of Japan and the Kuril Islands over the past 513 years. Okay, so with different magnitudes of earthquakes and tsunami over 10 meters. And we can count these. So over the past 513 years, 16 tsunamis with maximum height above 10 meters were induced by earthquakes of magnitudes between 7.4 and 9 meters. Now we use a simple probability. If we model the occurrence of tsunami as a Poisson process, the mean rate of occurrence, lambda, is 16 tsunamis over 513 years. So we have so many tsunamis over 10 meters a year. The return period is 1 over lambda, so that's 32.1 years. And so we can evaluate the probability of having at least one tsunami with maximum height larger than 10 meters in a T-year period is given by this using Poisson distribution. So 1 minus e to the minus lambda t. Lambda is this value. So in a 30-year period, the probability of having at least one tsunami above 10 meters is 60%. Over 50 years, almost 80%, and over 100 years, 96%. So the conclusion is the earthquake was extremely massive. The focal area extending above 400 kilometers long in the north south direction and about 200 kilometers wide in the east-west direction, caused magnitude multiple ruptures of seismic sources. At units 2, 3, and 5 of Fukushima Daiichi nuclear power stations, the acceleration response spectrum of seismic ground motion observed on the base mat exceeded the design basis. Although damage to external power supply was caused by earthquake, no damage caused by earthquake to systems, equipment, or devices that are important for nuclear reactor safety has been confirmed. Okay, so as we have seen, the design against tsunami has been based on tsunami folklore and indelible traces of tsunami, not on adequate consideration of the reoccurrence of large-scale earthquakes. The assumption on the frequency and height of tsunami was insufficient. Therefore, measures against large-scale tsunami were not prepared adequately. The seawall was not high enough, and the other emergency measures for emergency power were not in place. Okay, now let's look at a video, and it shows put everything together, and I edited this video from different sources.
One of our planet's most volatile regions is the Pacific Ring of Fire, a continuous fracture in the Earth's crust which circles the Pacific Ocean. At 2:45 p.m. on March 11th, 2011, 80 miles off Japan, one section of this fault is about to rupture. There is no sense of what's about to happen. But 80 miles out in the Pacific Ocean, and 20 miles down inside the Earth's crust, the Pacific Plate is being forced down underneath Japan. Solid rock twists and cracks. Stresses build up in the system until something snaps.
Shockwaves radiated out. The fastest, known as P waves, traveled at 6 kilometers a second. "100 seconds since the fault line slipped. The slowest moving but most destructive S waves reached Tokyo.
In Japan, the earthquake even rattles the most safely guarded installations. Just 90 miles from the fault line stands Fukushima Daiichi nuclear plant. With electricity cables damaged, emergency systems kick into action, engaging backup diesel generators for power, and beginning the shutdown sequence for the plant's 3 active nuclear reactors.
After shutdown, emergency diesel generators kicked in to pump coolant through the reactor cores. Fukushima survived the earthquake intact, but there was one big problem. It stands just meters from the sea.
But 80 miles out to sea, the earthquake has unleashed an even more terrifying force. And it's rippling outward at 500 miles per hour. And this is exactly what the quake triggered. When the Earth ruptured, 250 miles of ocean floor thrust upward over 20 feet. This displaced 3.4 trillion cubic feet of water in the ocean above, causing a surge that initially travels at 500 miles per hour. When the tsunami approaches land, it slows dramatically. But as the sea becomes shallower, the waves rise higher and higher, reaching up to 45 feet tall. The tsunami wave doesn't stop until it reaches 6 miles inland.
A massive aftershock has hit Tokyo, magnitude 6.2. In the week that followed the main quake, there were over 500 aftershocks along the fault. This is the actual data from seismometers around Japan. The larger the circle, the bigger the aftershock.
Japan has suffered 2 deadly blows. First earthquake, and then tsunami. But a third disaster is about to strike, as the nation faces potential nuclear meltdown. At 3:42 p.m., just 56 minutes after Japan is rocked by one of the top 5 earthquakes in recorded history, the tsunami wave approaches Fukushima Daiichi nuclear plant. Inside are 3 active nuclear reactors. Diesel generators are pumping water around the reactors to cool the nuclear fuel rods. But these generators must stay dry. The plant is protected by seawalls 18 feet high. But they are no match for the 45-foot wave. Filmed just after the wave has hit, this astonishing video shows the damage. Swamped by the wave, the diesel generators are destroyed. Now, there is just one backup cooling system left: battery-operated pumps. But they only have an 8-hour charge, and the clock is ticking. While Fukushima edges toward nuclear meltdown, across Japan's east coast, people are fighting for their lives. At its highest measured point, the tsunami reached 124 feet above sea level. But Japan's nightmare is about to get even worse. At Fukushima nuclear plant, the battery-operated cooling pumps run out of power. And then, seismic event turns into nuclear catastrophe. An explosion blows the roof off Reactor Building 1. 2 days later, another explosion hits Reactor Building 3. The Fukushima radiation leak is eventually given the maximum nuclear disaster rating of 7. The same as Chernobyl. This is the biggest disaster to strike Japan since World War II. And it's an event that has affected the whole Pacific region.
Now let's look at the characteristics of earthquake ground motions. Earthquake engineers are interested in strong ground motions, that is, motion of sufficient strength to affect people and their environment. At a given point, ground motions produced by earthquakes can be completely described by three components of translation: two in the orthogonal horizontal directions and one in the vertical direction. So for example, east-west, north-south, and vertical directions. And three components of rotation, but it's usually neglected in practice because they are not significant and very difficult to measure. For engineering purposes, three characteristics of earthquake motion are of primary significance. The first is the amplitude. How large is the ground motion? And the frequency content. What frequencies are important, as we studied in structural dynamics? And the frequency or the frequencies of the excitation is very important to the response of a structure and the duration of the motion. Okay, so it is therefore important to identify a number of ground motion parameters that reflect these characteristics in a compact and quantitative form. So here we have the ground acceleration recorded in the Imperial Valley earthquake in 1940. If we integrate, we get the ground velocity. And if you integrate again, you get the ground displacement. Now, if you compare these three figures, acceleration, velocity, and displacement, you can see acceleration time history shows a significant portion of relatively high frequencies. And since integration produces a smoothing or filtering effect, velocity time history shows substantially less high-frequency motion than the acceleration time history. And the displacement time history is dominated by relatively low-frequency motion. And in this figure, we have the ground motion time history for the acceleration, and this is the maximum ground acceleration, or called peak ground acceleration, PGA. PGA is the most commonly used parameter for describing ground motion, the maximum ground acceleration, because of the relationship between acceleration and inertial force. Because inertial force is m times a, acceleration. In design practice, it is usually assumed that the peak ground accelerations in the two horizontal directions are the same. The maximum vertical acceleration is assumed to be 2/3 of the peak ground acceleration in the horizontal directions. The largest dynamic force induced in certain types of structures, very stiff structure, are closely related to PGA. We will study this next when we look at ground response spectra. Okay, so PGA is a very important parameter. Now, if we integrate once, we get velocity, and the maximum ground velocity is called PGV, peak ground velocity. Since the velocity is less sensitive to high-frequency components of the ground motion, peak ground velocity can characterize ground motion amplitude more accurately at intermediate frequencies. Okay, so not too high, not too low, intermediate. For structural systems with dominant intermediate frequencies, such as tall or flexible buildings, bridges, the peak ground velocity provides a more accurate indication of the potential for damage than PGA. Now, if we integrate again, we get a displacement. Now we have peak ground displacement. Peak ground displacement can characterize ground motion amplitude more accurately at low frequencies. You can see the frequency is quite low. For flexible structural systems with dominant low frequencies, the peak ground displacement provides a more accurate indication of the potential damage. Okay, we'll look at the response spectrum in a moment. And now the duration. Before the earthquake, the ground was at rest, and sometime after the earthquake has stopped, the ground is also at rest. Okay, so we use Bragg duration to define the duration of the earthquake. The Bragg duration is defined as the time between the first and the last exceedance of a threshold acceleration, for example, 0.05 g. Okay, so when it reaches this threshold, we start counting the earthquake. And then when it goes below this threshold, then we stop. So we say the duration of the earthquake is this long, because in engineering practice, we are not interested in small ground motion, very small ground motion. Okay, there's this is on the notes, page 58. Because PGA is considered as a random number of strong motion process, the sum of all the squared acceleration values from a strong motion record can be used as a more reliable parameter to represent the amplitude of a strong motion record. And it's defined by the area's intensity given by this equation. Okay, so here A is the acceleration, A squared is somehow related to energy. And then we integrate it from 0 to t. T is the duration of the earthquake. Okay, so this is defined as the area's intensity. It's a very important parameter. Now, if we make a plot of the area intensity with time, so instead of the total energy, we plot it by changing the time t. Then, divided by the total energy, we obtain a cumulative normalized area's intensity plot. And this is called a Hussite plot. Okay, it serves to identify the interval over which the majority of the energy is imparted. Okay, so this shows the east-west component of the 1940 El Centro earthquake, a very well-known earthquake. Okay, acceleration with PGA 0.21 g, and peak ground velocity 31 centimeter per second. Peak ground displacement that much. Okay, so the area's intensity over 53.45 seconds. It's the total length of the record. Okay, is that much. And then we plot the Hussite plot, so you can see the energy changes from 0, and then it builds up to the total 100% of the total energy of the earthquake. Okay, now you can see the change of energy, and we call this evolution. Of energy, okay? It goes like this. Now we define some duration. A popular definition of strong motion duration Tm in nuclear industry is T 5 to 75. So that means the time span between 5 and 75% of the area's intensity, or T 9 to 95. It's the time span between 5% and 95% of the area's intensity. Okay, so 5% is here, and 75% here. So this gives us the 5 to 75 duration. It's 19.87 minus 2.14 seconds. Okay, so for between 5 and 95, 95 is 26.29. Okay, so that gives us the duration. So you can see if you use 9 to 95, that means 90% of the energy of the earthquake is spent over this period. Okay, so the duration here is about 24 seconds. Now I ask you a question. Suppose we have this, and not this. What does that mean? Okay, so now we will take a break. Now it's 56. So please come back at 9:06, 9:05. Okay, please come back at 9:05. During the break, please think about these two cases. And if you have an earthquake like this or like this, are they good earthquakes? Okay, so we have a break now.
哎，谢教授。
来，柯老师什么？
哎，谢老师你好，就是刚才你介绍了这个从加速度积分到最后到这个位移
啊，然
后呢，这个里头在做数值计算的时候，有时候会出现这个所谓的baseline 需要 baseline correction， 对吧？
啊，对对。
哎，对，你等一下可以稍微介绍一下这个。
行，我可以加这个进去，没问题。好。 Okay, welcome back. If we have Hussite plot, like the blue line, that means we will reach 95% of the energy. In a very short time. So the time history might look like something like this. So very small and then large motion, and then it dies down. Okay, so that's an earthquake of relatively short duration. And as we know that for a structure with long period or low frequency, it takes a long time for it to be excited. For example, if you have a structure with a frequency equal to 0.1 hertz, that means the period is 10 seconds. Okay, so for sine function, 10 seconds, 20, and you have one sine, not a sine. Okay, so that's one period. So if you have a very flexible structure, then this earthquake of duration of less than 10 seconds would not be able to excite the structure. Okay, and similarly, for this case, you have very small motion and then it increases and then dies down. Okay, so we prefer, especially in analysis, you have an earthquake of a long duration so that it will excite all important modes of the structure. Okay, so in fact, codes and standards require that if you perform a time history analysis, the duration of strong motion must be larger than some value. And in nuclear industry, we usually would take 20 seconds of strong ground motion. Okay, so this Hussite plot gives you a very good visual how energy is distributed over time. Okay, and earlier we mentioned that when we integrate acceleration, we get velocity, and then we integrate velocity, we get displacement. When we perform the integration, there's a problem. That's very significant in earthquake engineering. Okay, so this deals with the consistency and drift of time histories. A set of time histories, acceleration, velocity, and displacement are consistent. If we differentiate displacement, we get velocity. If we differentiate velocity, we get acceleration. Or if we integrate acceleration, we get velocity, and integrate velocity, we get displacement. Okay, so this is usually true, or always true in physics. A set of time histories are not consistent or are inconsistent when one or more of these conditions are not satisfied. And for seismic analysis and design of nuclear power plants or any engineering structures, the ground is at rest before and after an earthquake. Therefore, earthquake ground motions must satisfy initial and terminal at rest conditions. So acceleration, velocity, and displacement are all zero at the beginning of an earthquake. And they are all zero at the end of the earthquake. And the drift is a phenomenon that's observed, which means the time history is not at rest at one or both ends. Why would that happen? In analysis, we usually need all three time histories: acceleration, velocity, and displacement. Acceleration time history is important for dynamic analysis of structures, either linear structure or nonlinear structure, and in generating flow response spectra. And the velocity time history is important for sloshing analysis. That's when you have a tank containing water. When you shake the tank, the water sloshes inside the tank. And you can try this. You have a cup of water, and then you shake your cup, and then you can see the water sloshes inside the cup. Displacement time history is important for pseudokinetic analysis of multiply supported systems, for example, pipings in a nuclear power plant. Now, if the time history drift, we'll look at the drift in a moment, then it will give us erroneous results. If it's inconsistent, then we are obtaining responses to unrelated inputs. Okay, for real recorded earthquakes, we will have drift. This is usually due to ambient noises, threshold levels that used in the measurement tools, digitization of an analog record, and inaccuracy in a device. When we generate time histories that are compatible to response spectra, we will study this in a moment. We will have drift in time acceleration due to iteration or baseline correction in a long period wave, which will destroy achieved compatibility. Drift in generated velocity and displacement time histories are due to integration. If we integrate acceleration to obtain velocity, we will have drift. When we integrate velocity to obtain displacement, we will also have drift. And the phenomenon of drift was first reported by Hausner, but he did not offer any measures to remedy the situation. And Newmark standardized the baseline correction using polynomial. Okay, now let's see what happens. And this is a set of consistent drift-free time history. Okay, acceleration, velocity, and displacement. If you integrate acceleration to obtain velocity and integrate velocity to obtain displacement, you will have drift. Okay, so it's very obvious in displacement. In velocity, you also have drift. It's a very small, but it's there. You will have drift. So that means at the end of the earthquake, the velocity is not zero. And we have to use baseline correction to bring the end to zero. Okay, now let's see what happens. Let's say we look at acceleration time history AT with 0 at both ends. Okay, so now if we integrate acceleration, we will have one constant of integration. And if we integrate again, we have C1t plus C0. Okay, so that's very easy from calculus. But we have four initial conditions, four initial and terminal conditions for velocity and displacement. Velocity and displacement must be zero initially, and they must be zero at the end. But we only have two constants, C1 and C2. We have two constants, but we have four conditions. So that means the problem is mathematically overdeterminated. And if you specify initial zero conditions, you can determine C0 and C1 to be zero. Okay, but V and T may not be zero at the end of earthquake. That gives us drift. Now let's look at a simple example. For example, we have AT is T times 1 minus T. Okay, so acceleration is a parabola, 抛物线. And we integrate the acceleration, so we have one constant C1. We integrate again, we have another constant C0. So again, we have four initial and terminal at rest conditions, but we only have two constants. If we specify that the earthquake must be at rest initially, then we find C1 and C0 are both zero. Then the velocity and displacement are given by these two equations. Okay, so at the end of the earthquake, T equal to 1, V1 is 1 over 6, not 0. D1 is 1 over 12, not 0. So that means both the displacement and velocity drift. We apply Newmark baseline correction. That means we add a term minus T over 6 This will give us 0 at both ends. But if you differentiate velocity, you have this, and with an extra term minus 1/6. So the derivative of velocity is not acceleration. Okay, so this page shows that through integration, we will have drift in velocity and displacement. If we apply baseline correction, then the time histories are not consistent. That means the derivative of velocity will not give us acceleration. So that this is acceleration. When we integrate, we obtain the velocity at the drift. And we integrate again, we obtain displacement. It also drifts. We apply baseline correction. Now they don't drift, but they are not consistent. Okay, so drift and inconsistent time histories give erroneous results if you use it in simulation. And the problem is due to overdeterminacy in the constants of integration. We have 4 conditions for velocity and displacement, but we only have 2 constants. The baseline correction will introduce a large long period wave and may destroy the compatibility, or we will discuss compatibility later. A baseline correction renders corrected time history no longer mutually consistent. That means the derivative of velocity is not acceleration. And the baseline correction distorts the frequency content because you add a new wave. Okay, although baseline correction is endorsed by codes as a standard procedure for eliminating drift, the shortcomings of baseline correction by using a polynomial may make the correction an unacceptable remedy. For the past few years, we have developed a method which will resolve the problem of drift and inconsistency. So if we have time, we will present this later, okay, at the end of the course. Okay, an earthquake has 2 most important parameters. One is magnitude, the other is distance. Much of the energy released in an earthquake takes the form of stress waves. The amount of energy released is strongly related to the magnitude. We have seen this. The characteristics of stress waves are strongly related to magnitude. So magnitude is an important parameter. And the second is distance. As stress waves travel away from the source of an earthquake, they spread out and are partially absorbed by the materials they travel through. Energy per unit volume decreases with the increasing of distance from the source. Okay, so earthquake energy decreases when the distance is increased. Therefore, the characteristics of stress waves are strongly related to distance. So seismologists have developed many models to relate the ground motion with magnitude and distance. And this diagram shows that you have various measures of distance. So for example, we have the focus or hypercenter of earthquake shown by this star, okay? So right above on the ground, it's called epicenter. And this big red area is the rupture surface. And then you have the high stress zone. And this is the site of interest. So you can see we can have different distance from the site to the epicenter, from the site to the epicenter, from the site to the high stress zone, and also the perpendicular distance from the site to the fault plane. And seismologists develop something called predictive relationships. That's y equal to a function of magnitude m, distance r, and some other parameters. Okay, so here y is the ground motion parameter of interest. It can be peak ground acceleration, peak ground velocity, or peak ground displacement. And the peak ground acceleration is the most used parameter. And m is the magnitude, r is a measure of distance, and pi are other parameters, such as those used to characterize the earthquake source, wave propagation path, and local site conditions. And normally, regression relationship is developed in terms of the ground motion parameter y, magnitude m, distance r, and other parameters. Okay, two widely used prediction equations are given by Abrahamson and Silva, Atkinson, and Ball. And the regression model gives us the expected value. And in general, we need to consider the uncertainties in the predictive relationship. Okay, so the probability of the ground motion parameter larger than some threshold value has a log normal distribution. And we need the median value and standard deviation to characterize the uncertainty. Okay, we will not study this in detail because this work is done by seismologists. Okay, now we introduce the most important measure of earthquake. It's the ground response spectrum. We consider a single degree of freedom system under the excitation of ground acceleration, UG double dot. G stands for ground, and U double dot is acceleration. So UG double dot is ground acceleration. If you look at a single degree of freedom system placed Okay, so we have a single degree of freedom system with damping zeta and frequency T1 placed at the site. Now you have earthquake of ground acceleration UG dub coming in. It will excite the single degree of freedom system. We can find the response. Okay, so using Duhamel integral, the response is given by this expression. For lightly damped system, zeta is very small, usually 5% for civil engineering structures. And omega d, the damped natural frequency, is approximately the undamped natural frequency. In earthquake engineering, the negative sign is not important. So if we neglect the negative sign, and we find that the displacement is given by this expression, velocity given by this expression, and acceleration. Here, x is the relative displacement, and xa is the absolute acceleration given by this. Okay, so if you look at these three integrals, they are very similar, except we have cosine here and sine for these two. Okay, so approximately these three integrals are the same. And we have 1 over omega for displacement and minus omega for acceleration. Now we define relative displacement as the maximum relative displacement. We call it the displacement spectrum. So S stands for spectrum, D for displacement. The maximum velocity is the relative velocity spectrum, and the maximum acceleration is the absolute acceleration spectrum. If we evaluate something called pseudo-velocity response spectrum, that's this yellow integral, but we change cosine to sine. Okay, we change cosine to sine, evaluate this, then the displacement is 1 over omega of the pseudo-velocity spectrum, and acceleration spectrum is omega times the pseudo-velocity spectrum. So if we perform this integration to obtain pseudo-velocity, we can find the displacement and acceleration spectra. Okay, so this shows that we have a series of single degree of freedom oscillators or systems of some damping value zeta 1, but different periods, T1, T2, T3, we find the response, and the maximum response gives us the plot And this plot is called ground response spectrum. If this is velocity, then it's a velocity response spectrum. If it's displacement, then it's displacement response spectrum. Usually we use acceleration, and it is acceleration response spectrum. Okay, now let's look at example El Centro earthquake. We have looked at this before. Okay, we scale it to PGA equal to 0.35 G. So that's the maximum peak ground acceleration in the north-south direction. And we use a series of single degree of freedom oscillators, T equal to 0.1, 0.2, 3, and 4. And we find the response, pick the maximum responses, and then plot. Okay, so it's a little bit hard to see. Maybe I blow it up. I don't have my magnifier. Okay, anyway. Okay, so maybe look at here. For T equal to 0.5, the value is 2.02.
教授，又暂停了，屏幕。
又暂停了啊。Okay, so we don't have 0.5. So let's say 0.4, it's 0.956. Okay, so 0.4, 0.956. So when you do this, you will get a curve. Okay, this curve is called displacement response spectrum. And multiplied by omega, we get a velocity spectrum. And multiplied by omega again, we obtain acceleration spectrum. Okay, and the relationship between omega and period is omega equal to 2 pi over t. And some people like to plot in terms of period. Some likes to plot in terms of frequency. Both are okay. Okay, so you have to be familiar with both. In terms of velocity, or in terms of frequency or period. And we can see that the relationship between velocity spectrum and displacement spectrum is given by this equation. If we take log 10 of both sides, we get this. Okay, so now if you fix SD, so the black term is a constant, then this red term and this red term gives us a straight line. Okay, so for a given value of the black term, displacement, log of velocity spectrum and the log of period is a straight line of slope negative 45 degrees because of this negative sign. Okay, so we have this plot. The horizontal axis is period. Vertical axis is velocity, okay? And the negative 45 degree lines are these red lines, okay? They have slope of negative 45 degrees. Now they have a special property. If T and STD has a fixed ratio, if SD and T has a fixed ratio, then the value of S is fixed. Okay, so for example, T and SD, the ratio is 1. The ratio is also 1. The ratio is 1. Okay, so let's look at it. That means T is 0.1 here. Corresponding to SD, displacement 0.1 gives us this point. Displacement is this line. Okay, so 0.1 is this, and the corresponding velocity is 6.28. When T is 1, and SD is also 1, the corresponding velocity is the same. T is 10, velocity as displacement is 10, velocity is the same. Okay, 6.28. Now let's look at the relationship between velocity and acceleration. If we take log of both sides, we get this relationship, okay? Similarly, for the black term, it's acceleration. If we have a fixed acceleration spectrum, SPA, then the two blue terms give us a family of straight lines of slope 45 degrees. Okay, so these blue lines have slope of 45 degrees. And if we look at the ratio, not the ratio, the product T and acceleration, if it's fixed, then S is fixed. Okay, so here 0.01 times 10, it's 0.1. 0.1 times 1 is 0.1. 1 times 0.1 is also 0.1, and so on. Okay, so for T equal to 0.1, acceleration is 1. Acceleration is this axis. 1, it gives us 6.14 for velocity. For 10, okay, 10 here, period, and acceleration is 0.01. We have the same velocity. Okay, so we have these lines and these lines. Now we put them together. We have something called a four-way log plot or tripartite. 中文是三连图 or 三连图. Okay, so the horizontal axis is period. Vertical axis is velocity. This axis is displacement. This axis is acceleration. Okay, so we can plot all this in one graph. So for example, for period of a single degree of freedom oscillator, 0.64, you come here, you have this point. Okay, so the maximum ground acceleration, the maximum velocity response is 30.2. The maximum acceleration response is 0.78 g. And going this way, the maximum displacement is 3.03 inch. Okay, so we can plot a four-way log plot given a period. We can find the maximum displacement, velocity, and acceleration from this plot. And this is the plot for damping 0.05. Now, if our single degree of freedom systems have different damping, we will have different curves. Okay, so here the green curve is for damping 0. The pink curve, 5% damping. The blue curve, 10% damping, and the black curve, 20% damping. So that means for different damping values, the single degree of freedom systems would have different responses, and that we know for sure. Okay, now let's look at the behavior of the single degree of freedom systems. For a very short period, t less than 0.03 second, or very high natural frequency, f larger than 33 hertz. So that means in this red region, the system is very stiff because the frequency is very high, or essentially rigid. The system moves rigidly with the ground. That means there is very little relative displacement between the mass and the ground. Okay, so because this is very stiff, there's no relative displacement between the mass and the support. Okay, so you can see the displacement is the same as the ground displacement, and it's very small. Okay, the displacement, this axis, very small. Okay, almost zero. And acceleration approaches peak ground acceleration, and displacement is extremely small. For the other extreme case, for very long period, t larger than 33 hertz, or natural frequency less than 0.03 hertz, this red zone, the structure is extremely flexible. Okay, so the mass does not move, only the ground moves. The mass would remain essentially stationary. The relative displacement is the displacement of the ground. Okay, so in this case, acceleration is extremely small because the mass does not move, and the displacement approaches the maximum ground displacement. So if you look at acceleration, it's this axis. So you can see the acceleration value is very small. Okay, these values. And displacement reaches the peak ground displacement. And somewhere in the middle, for intermediate period or frequency, so t between 0.5 and 3 seconds, or frequency between 0.33 and 2 hertz. And the velocity is very large. Okay, so this is the velocity axis. The velocity value is very large, and it's larger than the peak ground velocity, this red dashed line. So the velocity spectrum may be approximated by a straight horizontal line. So the pink curve can be approximated by this horizontal pink dashed line, by a straight horizontal line amplified by a factor alpha v. So it's equal to peak ground velocity times amplification factor alpha v. I think we take a short break. Please come back at 10. Okay, let's continue. Now we introduce Newmark elastic design spectra. Newmark described idealized seismic response spectrum based on response spectra generated from a number of available earthquake records. This idealized seismic response spectrum was then further developed into a design. 又暂停了啊。Okay, this idealized seismic response spectrum was then further developed into a design response spectrum for structural design. Okay, so what we do here is we have our four-way log plot or the tripartite. We determine the peak ground acceleration based on probabilistic seismic hazard analysis, PSHA. We might introduce if we have time. And then we determine the peak ground velocity and the peak ground displacement using empirical formulas. Okay, so peak ground acceleration and peak ground velocity and peak ground displacement. Okay, so you can see the vertical axis is velocity. So, velocity. So that's peak ground velocity. And this axis is peak ground is acceleration. So peak ground acceleration goes this way. And this axis is displacement. So peak ground displacement has this value. Okay, so we draw these three lines and connect them. Now from TB equal to 1/8 second, we draw a line parallel to the peak ground acceleration with amplification factor of alpha A. So that's alpha A times the PGA. We have line 2. And then we draw a horizontal line parallel to the peak ground velocity and with an amplification factor alpha V. Okay, so the blue line, and then we draw the pink line parallel to the PGD line with an amplification factor alpha D. And then we trim off the lines to obtain this. Okay, then up to TA equal to 1/33 seconds, we have this line 5, which is along the PGA line, and above TF equal to 33 Hertz, we draw this line 5 along the PGD line. Okay, and then connect 4 and 5 and 2 and 5 using the green lines. And this is the idealized response spectrum. And we know that there's a great variability in response spectra for different earthquakes. So we need to normalize the response spectrum before calculating the amplification factors. We normalize to PGA for high frequencies, normalize to PGV for intermediate frequencies, and normalize PGD to low frequencies. Okay, we introduced why we use PGA for high frequencies and PGD for low frequencies earlier tonight, this morning. In 1973, Newmark used 28 horizontal ground motions and 14 vertical ground motions to determine the amplification factors. And this table is a list of the earthquake records. They are all from west coast of US, okay, mainly from the California area. And the magnitudes range from 5.3 to 7.4 and the different site conditions. Okay, so now we normalize the ground motion to PGA 0.22G. Okay, so PGA 0.1, that's 0.2. So this value is 0.22. Okay, so we normalize all the response spectra to PGA. So they all have the same start here. And then you can see large variation in other frequencies. Okay, so now we plot the median value of these 28 response spectra in red, and blue is 84.1%. That's the mean value plus 1 standard deviation. Okay, now you can see in this region, the curves are quite smooth. So we use the dashed lines to straight lines to approximate them. Now for the intermediate frequencies, we normalize to PGV equal to 0.195. Okay, so PGV here come to here. This value is 0.2, so very close, 0.195. Okay, then we plot. You can see the 50% curve and 84.1 curve. And in this frequency period, we approximate by horizontal lines. And then for long period, we normalize to PGD to this value, okay? And then similarly, the two curves, and then we idealize the curves by straight lines. Okay, so now this figure shows the idealized straight lines, and we can find the amplification factor because we know this value and we know PGA, so we can determine the amplification factors. Okay, so the amplification factors can be determined using these expressions, and they have been adopted in many design codes. For example, NUREG is the US Nuclear Regulatory CR0098, and ASC, American Society of Civil Engineering 498, and APRI code. Okay, so we use these amplification factors for different damping values. So now this is a standard obtained from west coast of USA. We can also obtain site-specific design ground response spectra. The design ground response spectrum should, in general sense, be constructed based on ground motions recorded at the site of interest during past earthquakes. So if you have a number of recorded motions, you can perform the same analysis to obtain site-specific design ground response spectra. But in many cases, it's not possible because we don't have sufficient earthquake records available. So we can use standard design response spectrum. Okay, so we can use the these values. And different standards have different shapes. For example, in Canada, the Canadian Standard Association has a set of design ground response spectra for nuclear power plants in Canada. And Chinese HAF also has a set of design response spectra. Okay, the design ground response spectrum have different control points and amplification factors. These values, these corners are called control points. Okay, so in this case, we have 33 Hertz, 8 Hertz, 1/10 Hertz, and 1/33 Hertz. And different codes may choose these frequencies or periods differently. Okay, so these are called control points. And if you use different earthquake records, you will find different amplification factors. And I'll give you an example. For example, the Canadian Standard Association used earthquakes anchored at 0.1 G PGA, and we used 84.1% a curve. So that means mean plus 1 standard deviation. And the PGA values are given by this for different site conditions, rock site, overburden site, okay, from empirical values. And they obtained the amplification factors for different damping values, alpha D, alpha V, and alpha A. So this is a plot of the response spectra. Damping 0, 2%, 5%, and 10%. Now you can see we have different control points. And in terms of frequency, 0.02 Hertz, 0.08 Hertz here, and 7 Hertz for this, and 33 Hertz here. And these two values are determined by the intersection of these two lines, okay? Now in engineering practice, there are two very important characteristics. One is the spectral shape. You can use the Canadian shape or the Newmark shape. And they characterize the frequency content. And then another is the amplitude. It is governed by the seismic hazard level at the site of interest. For example, here the PGA value is that's 10. Okay, so 10% G ground acceleration or 0.1 G PGA. Okay, so the graph is scaled to 0.1 G. For your site of interest, you have to determine the PGA value and then scale the spectrum. So it's first important to determine the spectral shape. It depends on which code you use. So in China, we will use the Chinese code. In Canada, we use the Canadian code. A conventional seismic design spectrum is the product of the standard design spectral shape and the peak ground acceleration. Okay, normally peak ground acceleration is determined by probabilistic seismic hazard analysis, PSHA, for your site. And then you scale the standard design ground response spectrum with the obtained site PGA. Then you obtain the DGRS for the site of your interest. Okay, so now this shows different response spectrum. The blue line is the Canadian Standard Association, anchored at 0.25 G. The pink curve is the NURAC, U.S. Nuclear Regulatory 0098, anchored at 0.3 G. The red is for the Qingshan Nuclear Power Plant in Zhejiang Province, 浙江省的秦山, and it's site-specific to the Qingshan site. And the red is the horizontal spectrum, anchored at 0.15 G. The black dashed line is for the vertical direction. So in this case, the horizontal and vertical response spectra are not the same. Okay, they have different shapes, all anchored at 0.15 G. Okay, now let's look at the three directions. We have two horizontal directions and one vertical direction. These three directions are mutually orthogonal. Okay, they are perpendicular to each other. Normally, we assume that the two horizontal directions are the same for these two cases, but for Qingshan, they are different. And the vertical component is 2/3 of the horizontal component. So PGA in the vertical direction is usually taken as 2/3 of PGA in the horizontal directions. And the vertical and the two horizontal earthquake ground motion time histories should be statistically independent. And if you perform analysis, they should be input to your structure simultaneously at the same time. Okay, there are some disadvantages for the NUMAC spectrum. We mentioned that you can have a standard shape or site-specific shape. It's very difficult to develop a site-specific NUMAC spectrum because we need a large number of earthquake records. And these records should be near the site of interest and recorded at sites with similar geological and site conditions. And it's not possible for northeast of North America. Okay, so for example, in Ontario, in Toronto of Canada, we have very few earthquakes. We don't have enough number of earthquake records to develop site-specific spectra. And it's the same as in Jiangsu province of China. There are very few earthquake records. Okay, so not possible for many regions. For example, northeast of America and Jiangsu province of China. So if you are not able to develop a site-specific spectra, a potentially inappropriate spectral shape may be used. When NUMAC developed the standard spectral shape, he used 28 ground motions. 22 of them are from soil sites, 6 from rock sites, and 7 of 9 earthquakes have magnitudes larger than 6.0, and a number of spectra from the same earthquake For example, 8 of 28 records are from the 6.6 San Fernando earthquake. Okay, so if your site condition is different from California, you may use the wrong spectral shape. Okay, so to resolve this problem, people have developed a seismic hazard analysis. Seismic hazard analysis involves the quantitative estimation of ground shaking hazards at a particular site. There are two methods. One is deterministic, called deterministic seismic hazard analysis, or DSHA, or probabilistic seismic hazard analysis, PSHA. Okay, for DSHA, deterministic, we assume a particular earthquake scenario. And for probabilistic PSHA, the uncertainties in the earthquake size, location, time of occurrence are considered explicitly. Okay, we don't have much time, so I will go through this quite quickly. Deterministic seismic hazard analysis was used in the early years of geotechnical earthquake engineering. We assume a particular earthquake called controlling earthquake. So for example, the star is the site. Around the site, we have different sources. Source 1 is a point source. Source 2 is a line source. And source 3 is an area source. Okay, so we have different distances. And so for the worst case, we use the shortest distance between the site and the source. Okay, so we use the shortest distance for the worst case. And we have also different magnitudes for the sources. So for example, for source 1, we have the regression equation that we mentioned earlier, log y in terms of distance and magnitude. Okay, so for source 1, we have this curve. For source 2, we have the blue curve. 3, we have the red curve. Okay, then we have these distances. Now you can see source 3 gives us the maximum ground motion parameter. So we use this as our controlling earthquake. So we use the third earthquake to determine our seismic hazard at the site. And we can determine the peak ground acceleration, peak velocity, and response spectrum. Now this method is the worst case scenario because we use the shortest distance and maximum magnitude, okay, to obtain the maximum ground motion parameter. And it is the worst case. It does not give us any information on the likelihood of occurrence of such a controlling earthquake. And the likelihood of occurrence at the assumed location, because that's the shortest distance. and expected level of shaking during a finite period of time. And all the uncertainties in all these analyses, okay? And so DSHA requires subjective opinions on some input parameters. To overcome this, PSHA, probabilistic seismic hazard analysis, has been developed. It provides a framework in which uncertainties in the location of earthquake, the magnitude of earthquake, rate of occurrence, and variation of ground motion parameters, such as PGA, with magnitude and location, can be identified, quantified, and combined in a mathematically rigorous manner to obtain a more complete picture of the seismic hazard of the site of interest. Okay, so first, we consider the uncertainties in the distance between the site and the source. So for example, for source 2, we have a uniform distribution of occurrence of earthquake along this line. Then we find the different distances. Okay, so that has this distribution. And for source 3, it can be occurring anywhere in this area. So we can find the distances, and that's the distribution. And we also characterize the temporal distribution. That means the occurrence of earthquake with time, and the probability distribution of earthquake magnitudes. Okay, so we model the magnitude. It occurs between M0 and some M maximum with this distribution. And so we can find the probability of the response spectrum larger than some threshold given a magnitude and given a distance. This is the predictive relationship that we mentioned earlier, developed by seismologists. Okay, and then the probability of exceedance of some on the motion parameters. Okay, so we combine all these uncertainties into a formula. Okay, so given earthquake magnitude and the distance, the probability of the ground motion parameter larger than some threshold is obtained from the predictive equation. And we have the distribution of earthquake magnitude, the distribution of distance, and the rate of occurrence of such an earthquake. Okay, so we combine these to find the rate of occurrence of y exceeding a y star value. And then we use numerical computation to discretize the magnitude, the distance, to evaluate this rate. Okay, so finally, we obtain something called seismic hazard curve. And this is a numerical example. We have a site and two line sources. For source 1, the earthquake magnitude is between 5 and 6. This is the rate of occurrence of an earthquake. And for source 2, magnitude between 5 and 8, rate of occurrence 0.09. Okay, so now if we have a single degree of freedom oscillator of period 1 second, this is the seismic hazard curve. What we have here is the probability that the response spectrum at 1 second exceeding 0.155 has a probability of 4 times 10 to the minus 4. Okay, so now for this level of probability of exceedance for a period of 0.1 second, the probability of exceeding this value is 4 times 10 to the minus 4. Okay, so now we can have a series of plots for different sites. Okay, this is the seismic hazard curves for some US cities. The horizontal axis is peak ground acceleration, and the vertical axis is the annual frequency of exceedance. So let's say peak ground acceleration. So the probability of exceedance 10 to the minus 3. Chicago is 0.01234, about 0.04 G. Okay, so Chicago is lower, and New York is higher, 0.12 G. And when you go to west coast of California, remember it's along the Ring of Fire, it's much higher, so it's 0.7 or 8 G. Okay, so this gives us the measure. So if you are designing building a structure in San Francisco with this level of probability of exceedance, 10.-3, you use PGA equal to 0.789, so about 0.7 G. Okay, so now if you need higher safety or lower probability of occurrence, 10 to the minus 4, then it's 1 G, okay, for San Francisco. Now it's time, so I will stop here for today, and we will continue next week. Thank you very much for today. Have a great day.
谢谢教授。
好，谢谢，再见。